of my dA vector, my magnitude of my dA vector? Well, I mean, so what are we talking about? I got two surfaces here, yes? Actually, one, two, three. We agree that nothing is in here, yes? So let's consider the outer surface, this part, and this part, and this part, right? So is there any flux at all through this part? We went over this yesterday. Why? The electric field skims the surface. It does not penetrate the dA surface, yes? So only the cap. Well, does this one have a fixed area? What is the area of the end cap?
Area
That
of
over what? Right, so you either write it down or you don't. It doesn't matter. But the integral over dA, by the way, what is the angle in that picture between my electric field and my patch and my dA? Yes, so cosine of 0 is 1. So look at it. Epsilon naught EA. So again, I don't necessarily need all these steps, but I do need an in-between step and some kind of explanation that you understand that the electric field must come outside of the integral because it's constant. Yes? Okay. So fairly straightforward. Finish Gauss's law and say, well, this epsilon now what? What do I want to find? Wait, what am I looking for? What am I looking for? I'm looking for the electric field close to that surface. I could be also looking for the enclosed zone. But I want to get to a formula for the electric field. I don't know, but I don't like this. How else can I put this? Give me something else. Give me more. What is this? Jets. So look how pretty. This is way pretty. That's it. So that is the electric field, 4 points, extremely, extremely close to a conducting, the surface of a conductor. Just outside the conductor is perpendicular to the surface and proportional to the surface charge density. So don't forget, the electric field is perpendicular to the surface and it's proportional to the charge density. What do I mean when I say proportional to the charge density? And does that make any sense? When something is proportional to something, tell me in words the relationship between those two things. It changes what? If that means if I increase the surface charge density, what happens to the electric field? Which kind of makes sense, right? The surface charge density is Q enclosed over epsilon. So I mean over A. So you know that if the Q enclosed is 5Q, you're gonna have some lines. But if it's 10, right? You're gonna have double the amount of lines steaming out. Yes? So now, let's do the same thing, but for an insulating sheet. And what I want you to look is, go back and look at this drawing. Look at the way we're setting this up. For an insulating sheet, this part is true, but you cannot then say that inside the insulating sheet is 0, right? So you would actually then have the other half of the cylinder to take care of, setting of Gauss's law. Yes?
Why is it 0?
Because we're dealing with a conductor. And we know that the electric field inside the conductor must be 0, which leads to there should be no charge enclosed, according to Gauss's law. Yes?
Is that only because of the pathway? Or
That is only because it's a conductor, and the conductor acts as a pathway for the charges. Yes. So, this is the picture now. Notice the difference between these two, which I thought it was a good idea to show you now how to do these. So, again, this is our sheet. It's insulating, so when I take this sheet and I give you a view of
negative, you just flip this.
We should be adding something or subtracting. Are we going to add? We only had this term before. So now, what is this term going to contribute in Gauss's law? It's going to add up? Is it going to be double? Is it going to be half? So let's see. So consider a cylindrical Gaussian surface. This is my closed interval in that dA, which gives me the net flow. So you agree with me, right? So not messy. I did a very good job on this slide, right? I wasn't messy. So let's not skip anything. So this is the end one. This is the end two. And of course, this is the side. Is it clear when I say the sides, right? This side, the rounded side of the cylinder. You know what that means? You're pulling us here, right? So let me make sure. So what we did yesterday, right, while you were trying to be here very hard, was this is one path, this is the other path, and this is that. The tobacco. That's it. So this is dA. It's always perpendicular and comes out of the surface. This is dA, and this is the rounded part of the cylinder. So dA must come out also perpendicular. So what we had is, if you look at that picture, the electric field is in the same direction as